over this stuff. If you have any questions, please ask. All right. So to finish the discussion, unfortunately, I won't have time much to review the last lecture. I'll just go through this bit of it quickly and finish the statement, the punchline that I was trying to get to. So last time we talked about the Noether current for non-abelian symmetries. In particular, we're talking about a UN global symmetry. Consider Lagrangian density where phi of A is an n-dimensional complex vector of fields, right? It's a vector, but it's not a vector under representation of space-time. It's an internal set of degrees of freedom, okay? So this is the action we write for it. It's the simplest action you could write down that's consistent with symmetries, is local and second order in derivatives expansion. So imagine that this V is like, if you expand to the first order to the second order, it will be half m squared phi dagger. All right. So this is the action. The symmetry group is UN. It's an internal symmetry. It's global symmetry. So upper and lower indices are different. Hopefully that is clear, right? That when the symmetry acts on the field, it transforms it. It acts like a matrix, right? It transforms like this, right? So this is, if it transforms like this, the field is in a fundamental representation. So the field phi is in the fundamental representation. It acts on the left, but phi dagger is in the anti-fundamental representation because it acts from the right. These two are conjugate representations. They are dual to each other, meaning that by just composing the two, you could get a scalar under the transformation, which is invariant. Good. Here, the fact that we're talking about unitaries has nothing to do with Wigner theorem, right? This is all classical physics. We just happen to have complex vector fields. All right. So this is a Lie group. UN is a Lie group. So we could write it in terms of this exponentiated form of Lie algebra for Lie algebras, and lambda k's are Lie algebra generators, and these are some infinitesimal parameters. Following Noether's first theorem, we get the Noether currents. Noether currents will be labeled by, so these are vectors in space-time, right? Noether currents are always space-time vectors. Why? What is the conservation law for a Noether current? Del mu J mu, right? So at least it's a vector. It could have other indices. But here, there's a label K. K is the label for the generator, right? So how many of them, what's the label K run over? Dimensionality of the group, right? 1 to dimensionality of the group. So here the generators are n by n matrices, right? So that's these are the currents. If I integrate such a current over a codimension 1 surface, I'll obtain a charge, right? So we'll see that in a second. I also made a comment about the adjoint representation. This is a setup where for representation matrices, you pick the representation matrices to be just the structure constants, right? So you could check that this forms a representation, and the dimensionality of this representation is the dimensionality of the group. So now the field expressed in this representation will have a component for every value of K. So I can write it this way, right? So it's natural to talk about phi ABs, right? A and B run from 1 to n, whereas K label runs from 1 to the dimensionality of the group, right? So this phi AB is a dim G size vector, right? But we're representing it in terms of n by n matrices with a bunch of coefficients. Good? Yeah.
Is this adjacent representation irreducible?
Adjoint.
Is it irreducible?
Is it irreducible? Anyone? Yes. For which group? For SUN.
It depends on groups.
Maybe it doesn't. No. Of course it's sorry. It's not. It's irreducible. It's irreducible.
Yeah, it always be reducible.
Yes. Sorry, I should have said that. Yes. All right. Good. The way it transforms, now that we write it, by the way, this is familiar, right? Like, for example, if I have U2, right? What's the dimensionality of that group? U2 is 4. What are the generators of the Lie algebra? Identity and the Paulus, right? When you write down a 4-dimensional, so the representation is 4-dimensional, right? So every matrix would have a form of this type, right? But when you represent it as a 2x2 matrix, this is precisely that story, right? Our object has 4 indices, so I can view it as A0, AX, AY, AC. But by packaging it this way, I'm writing it as acting with 2 labels, right? N by N. Questions?
That's why the L index goes from 1 to N squared.
Yeah.
So our echelon representation is always 2 like this, 2 indices?
No. So it's about how you write it. Here we want to act. So the reason that this is convenient is that the adjoint representation could be always written in a way that it looks like it's transformed. Its transformation could be written such that its action is fundamental on the left and fundamental on the right. So you could always do that, and that's what we do in physics. Just generally, that's how we do it, right?
It's a trivial question.
Yeah.
And here, the vector is 4 plus 1 matrix, right? So we are writing it in terms of the Pauli matrices, which are 2 plus 2. So are we taking direct sum?
No, there's no direct sum here. Yeah, it's just U2 4-dimensional representation. Right? Yeah. Good. All right. So now let's talk about the algebra of charges. I found the current. So all I need to do to find the charge for this UN theory is to integrate over codimension 1 surfaces. So I'm just going to pick it to be a constant time slice dd of x, right? And notice that there's matrix multiplication here, n by n matrices that have suppressed, right? So hopefully that's clear. When I write phi dot dagger lambda k phi dot, this means that this has an index A, this has an index B, this has an index B, right? These are indices that run from 1 to n. I can write this as a trace as well. Good. All right, so very good. Now, hopefully you recall from classical physics that we had the notion of Poisson bracket, right? And to every general coordinate, we had an associated conjugate momentum, right? And the Poisson bracket of those 2 guys, like for example, in field theory, phi of B, conjugate of it is pi of B. If you take the Poisson bracket, it's a Dirac delta function because you have a degree of freedom at every point, and then delta BA, right? The same way you could calculate the Poisson bracket of conserved currents. This is all classical physics, right? Conserved current with the field variable, and you find that it looks like the action of lambda on the field. So just a little bit of discussion, just 1 second, right? If this just to does this make sense? Do I need to explain it, or? If you have a field, right, the charge the charge exponentiated acts on the field and changes it, right? ddt of the field under this transformation, or dd whatever, lambda or theta, whatever is the parameter of your small deformation, would be the Poisson bracket. If that doesn't make sense, this is just a calculation. We could follow step by step. Then you see explicitly that if you calculate the Poisson bracket of two conserved charges, the Poisson, the conserved charges satisfy the Lie algebra. The Lie algebra of the group, if you think of, well, actually, Poisson bracket is a form of an anti-commutator, right? Classical physics, right? So conserved charges form a representation of the Lie algebra. Yeah.
But those Poisson brackets are functional Poisson brackets. They are not the usual ones. I mean, there's
What do you
functional differentiation in that way. Instead of partial.
So the phase space is more elaborate because you. So phi of A of X and pi of B of Y, there's a crazy large phase space. Yes, it's gigantic, but you could still calculate the Poisson bracket, right? I mean, these are the analogs of the Poisson bracket relations. It's just Hamiltonian formulation of classical physics, right? And in quantization, what we do is we send the Poisson bracket to 1 over IH bar commutator, right? But here, all I wanted to say is that now we've finished this triangle we were talking about, right? So we had differentiable symmetry transformations. Here we had conserved charges and currents, right? Here we're talking about representations of these symmetries, Lie algebras and Lie groups. The fact that the conserved charges with respect to the Poisson bracket form a representation of a Lie algebra finishes all these relations. One more important thing. What is a bracket? What is well, every time we talk about Lie algebra, the commutator operation or the Poisson operation should have a bunch of simple properties. I can write down all the defining properties. It has to be anti-symmetric. That's one. What other relation do you need? Jacobi identity. And Poisson bracket satisfies that. So the Lie algebras, the conserved charges form a representation. Sorry, are there any other questions? Question?
Yeah.
Okay.
Is that just as a clarity of mind, but those Poisson brackets are not do not involve partial or partial derivatives.
Are not what?
They do not involve the partial derivatives.
Did you?
Used to?
Did you? So it's just a standard Poisson bracket. Does anyone remember what the Poisson bracket is?
Yeah.
What's the definition of the Poisson bracket on the phase space? So if you have Q of P, yeah, exactly. Yeah.
But why shouldn't those derivatives be?
Allow just 1 second. Does anyone know what this piece is? Where does this come from? It comes from the volume of the phase space. It's a volume element of the phase space. It's basically, it comes from, I don't want to, we'll run out of time with that. There's a volume of the phase space that is being used. So there's a, just long story short, we start with a Lagrangian. You could do a Legendre transformation, build a Hamiltonian, right? Once you build the Hamiltonian, you could reformulate your equations of motion that we derived in the Hamiltonian language And you see, you could write and package it elegantly in the following sense that the by the way, what are classical observables?
Functions in this.
Smooth functions of the phase space, measurable functions of the phase space. So the evolution of classical observables would be the Poisson bracket of the object, the function with Hamilton. Right? This is just classical equation. It's equivalent reformulation for our Euler-Lagrange equations. For this whole story, it's crucial that the action is local in time. There's no way on earth otherwise you could do this, right?
But with no function, we don't need functional differentiation.
Of course you do.
So okay, so they're brackets.
It's dels. Yeah. Yeah. In quantum field theory, these are continuous variables, right? All right. So now we can, I'm going to ask one more time before starting lecture 10. Are there any questions about this? Oh, there was a question. Sorry.
The charges from the joint representation.
There are charges from the adjoint. That's what we calculate. So
They form the joint representation. Because yeah, it has the time dimensionality of the generator.
So sorry. No. What I did, let me tell you, let me summarize in words what the calculation was. I understand what I caused confusion. So what I did was the following. I said, let's consider a scalar field in space-time that transforms as a fundamental under a UN group, internal group, global chart. I calculated as conserved current and conserved charges, and I showed that the Poisson bracket of the corresponding conserved charges satisfies the Lie algebra of the UN. In the middle, along the way, because I was defining fundamental and anti-fundamental, I did a little detour, and I defined the adjoint representation. Yeah. Sorry about that. We'll come back. Well, the way we're going, we're not going to come back to QFT1, but QFT2 will. All right. Any other questions? Good. So let's get started. So all of this was to finally get to our most important group of all time, the Poincare group, right? So today we're going to start a new section of the course, chapter of the course, which is about representation theory of the Lorentz group. First start with the Lorentz group, then we talk about the Poincare group, okay? So to summarize, in part 3, what we talked about was the symmetry principle, right? We had this triangle. There was the differentiable symmetry transformations, Lie groups and Lie algebra representation, conserved charges, and we saw all those relations. All of this was for internal transformations, where your transformations had no space-time labels, right? When we're talking about this UN that we were just talking about, the UN acts at every point in space-time. The UN elements do not carry a space-time label, okay? I'm not teaching gauge theory, so I will not comment any further. But now we saw that we could have transformations that act on space-time, right? So that is going to be the context of the topic of discussion in this section of the course. We're going to be talking about space-time symmetries as opposed to internal symmetries. For now, internal symmetry is synonymous with global symmetry. Space-time symmetry is a space-time symmetry, all right? So this course is about Minkowski space RD, 1. The symmetry group is the Poincare group. So in part 5 of the course, we're going to talk about representations of the Poincare group, and we'll see that a particle will come out as a representation of the Poincare group. And this way we can also systematically describe different field theories in words, right? So if I want to describe a field theory to you, I say pick a field in such and such representation of the Poincare group, right? And then if I have internal symmetries, I'll describe also what representation will transform, right? And if I give you that data, and I tell you that write down the most generic action you could write down, that's second order in the field and second order in the derivative, you should be able to write it down. That's a free theory. Good? All right. So, just a little bit of terminology. Lorentz group can have projective representations, and that's where spinors come from. Poincare group cannot have projective representation. So we're going to be focusing on Lorentz representation first. Sometimes in physics literature or in the math literature, a projective representation of Lorentz group is called quantum Lorentz group. I don't like that terminology. I encourage against it. But sometimes you see this in some random papers, mostly by mathematicians, actually. Importantly, the Lorentz group has no central extension. Why was that? No, because there's no identity. It's SOD comma 1, right? So the fact that it doesn't have identity in it, it means that it cannot be centrally extended, but it can still have projective representation. If it could get centrally extended, that was the way to get projective representation, but there are other ways of getting it. So just go back to the beginning of the lecture. If the manifold is not simply connected, it can have projective representation. Previously, I had a comment about the Mobius strip, but I'm not going to say it. All right. Poincare group. So what is the Poincare group? It's a set of diffeomorphisms, right? Differentiable bijections from the coordinates to coordinates that leave the metric flat space invariant, right? So the flat space, here's a metric, flat space metric minus dt squared plus dxa dxa. And if you look at the flat metric, right, under a coordinate transformation, under diff, it transforms this way. Good. Now, we saw this, right, that this eta mu nu in some orthonormal basis, you could write it eta, you could view it as -1 plus. So I'm going to mess this up. What notation am I using? Oof. Oh, I'm using -1 plus 1 notation because I said minus dt squared. All right. So it should be clear that any matrix, any linear diffeomorphism that satisfies this is a symmetry, right? What is this group actually? This group is OD comma 1, right? So I've just written it here. Right? This is OD comma 1. And of course, on top of that, these are the Lorentz transformation. On top of that, I have the RD comma 1 as a group as well. Those are translations, right? We usually write it this way. It's called semi-direct product. If you don't know what it is, don't worry about it. It just means that take this group and add to it these generators and see what you get. All right, so sometimes the Poincare group is also called the inhomogeneous Lorentz group. This is terminology. I don't like that terminology either. So a Poincare group element, we're going to label it by a Lorentz element, lambda, and A, which is a 4 vector, or d comma 1 vector. Right? It's a group. It's invertible. Hopefully you can convince yourself of that. You could check that it's a group. Now, if I look at this equation, I see one thing. First of all, the determinant of lambda has to be 1. Sorry, the determinant of lambda squared has to be 1. Right? So there are two options. The determinant of lambda is either +1 or -1. These are real matrices, right? So OD comma 1 was the full group. If the determinant is +1 or -1, that's just, those are two disconnected pieces of it, right? And by fixing the sign of the determinant, you could pick one of them that we call SOD comma 1, right? It's a little bit more tricky, but let's first agree on this slide first before going to the next slide. Let's first make sure that we all understand this. Good? All right. Fields are going to transform as a representation of the Poincare group. It means what? It means that the fields would be some vector, would be valued in some vector space. And for every lambda and every A, there would be a matrix that acts on that vector space, right? That's a representation of the Lorentz group. It's an irreducible representation, right? If it's an irreducible action, the fields act irreducibly. Good. So these are representations. Like I called them S, but previously I was calling them R. If I have S of lambda 1A1, S of lambda 2A2, if I multiply them, this is what I get. Hopefully that's clear. Right? So now let's talk a little bit about the topology of OD comma 1, the Lorentz group. Let's first start with 3 plus 1 dimensions. So one thing that you need to know is the properties of the Lorentz group is different in even and odd dimensions. Good. So if you're talking about 3 plus 1, 1 plus 1, 5 plus 1, it's one story. If we're talking about 2 plus 1, 4 plus 1, 6 plus 1, it's a different story, right? And I'll tell this story. First, let's start with 3 plus 1 because that's what we like, right? And I'll come back and talk about 2 plus 1 or odd dimensions. Good. When you're in 3 plus 1, let's define OD comma 1 has 4 disconnected pieces. The disconnected pieces are like this. I already said that if the determinant is 1 and minus 1, they are disconnected, right? Let's first define a Z2 times Z2 worth of transformations. One Z2 is called parity. This is the one, this is a transformation that leaves x0 invariant, flips the sign of all space directions, right? This is called parity. This is the good. Is that good? You could check that this satisfies this equation, right? So what I'm finding is the following. I'm writing down 4 examples of these matrices, right? And this is one matrix, and there is a part of the Lorentz group that's connected to this. Then there is the parity transform version of it, this guy. They're disconnected. You can't go from this to that continuously. There is also, so now both of these, there is also this guy, which is not connected to either of them. And finally, there is this guy. These are 4 elements. We check that they all satisfy this equation, but they're all disconnected. And around each of, so this is the identity. Around this identity, there is a connected piece. Around this guy, there's a connected piece. There's a connected piece and a connected piece. The way to go between these two is time reversal. The way to go between these two is time reversal. To go from the bottom to the top is parity. Right? So there is a Z2 times Z2 worth of symmetries, potentially symmetries, transformations, right? That will go between these 4 pieces. Now here comes the question. Is this good? Does everyone agree on this? We can, how are we going to label them? No, actually. Oh, let me make a comment. So when we say relativistic quantum field, when we say relativistic fields, what do we mean? We mean that these lambdas that are connected to identity are symmetry transformations. But do we mean that the ones that are not connected to identity is also symmetry transformation? It's up to us. So the question of whether that question is equivalent to asking us, is the symmetry of space-time this? Or is it the part of this that's connected to identity? That's equivalent to asking, is the symmetry of space-time a part of this that's connected to identity and parity and time are symmetries or not? They need not be. Like, there are legitimately sensible field theories where parity is violated, time is violated. Those are sensible theories. This is a discrete part of the Lorentz group, right? That's why sometimes you hear about like time reversal symmetry breaking, blah, blah, blah. That's a question of whether this is the symmetry or is it the connected piece. The connected pieces of it better be a symmetry if you have relativistic physics, right? But P and T is up to us. Well, for different theories, we can cook up different things. Yeah.
So basically, it doesn't matter what of those four boxes we choose. We must have invariants or observables.
No, I'm saying that it's your choice. We would call something that has this piece. So, sorry, let me just say one thing. So usually we talk about the way we classify this stuff is through determinant of lambda, the sign of the determinant of lambda, and lambda 0, 0. The sign of lambda 0, right? Using that, we label all four of these guys. It's up to you. So the fact that this one piece of it that's connected to identity is a symmetry is the very definition of relativistic physics. Whether parity and time is a symmetry, it's up to you to decide. Well, like again, up to you means that you tell me what are the symmetries of the theory. I write down the simplest action consistent with those rules, right? Like this is what Landau taught us field theory is all about. You describe to me the field, the symmetries. I'm just gonna do in derivative expansion the simplest thing that's consistent with the symmetry. Transforming in some representation. Good. So parity and time have to do with disconnected or discrete, going between disconnected parts of the Lorentz group. Now, by now, I've actually been using the word Lorentz group as OD comma 1, SOD comma 1. So which one is it? Let's give them some names. We're gonna do the following. Let's call the piece that's connected to identity. That's the piece that has lambda 0, 0 equal to 1. And determinant of lambda is equal to 1. Let's call that group SO plus D comma 1. S because of the determinant that I picked to be plus 1. And lambda 0, 0, I pick it to be 1. I put the plus. So that is SO D plus 1. It's the proper orthochronous Lorentz group, but that's a mouthful. Let's call it the restricted Lorentz group. From now on, Lorentz group is going to be OD comma 1. The restricted Lorentz group is going to be SO plus D comma 1. Those of you guys who are okay, no, I'm not gonna make that. Good. Now, something funny happens when the dimensionality of space-time. So this is a story that I said that the dimensionality of space-time is even. When the dimensionality of space-time is odd, when you do a parity transform, right? Here, the determinant changed when I did parity transform. In odd space-time dimensions, under parity transform, the sign of the determinant doesn't change. So the odd dimensional Lorentz group, O2 comma 1, has only 2 disconnected pieces. Right? That is the beginning of the story of how you should be treating even an odd dimension separately. Most of what I say in this course is going to be specific to even dimensions. From time to time, I'll just throw out random comments about odd but you'll have to do the representation theory a little bit differently. It's famous that it's a little bit different. And I gave one indication, right? That's different. As a matter of fact, it's very important. You'll see in a bit that the representation theory Lorentz group is very much dependent on the dimension. Because, does anyone know why? So I picked this. Is this connected now? This is connected. So I can connect every 2 points continuously. But the question is it simply connected? Is there fundamental group? Is the fundamental group non-trivial? We'll see that in a second. The fundamental group is what leads to spinners and the non-triviality of it. And we'll see that it's very much dependent on D. There's no general formula in mathematics that we write down SOD, comma 1 plus as this fundamental group. We have to case by case. It's a difficult question in math. That's why we discuss them case by case. All right, but we'll see that. That's just a few steps ahead. All right, so from now on, we're going to be talking about the restricted or proper orthochronous Lorentz group. This is SO plus D comma 1. This is the piece that's connected to identity. One way to represent it says determinant is 1 and lambda 0, 0 is 1, right? Lambda 0, this determinant is 1 and lambda 0, 0 is 1. And then at some point later on, we'll come back and talk about, instead of talking about the other group, the other pieces, we talk about is time translation and parity symmetries, right? That's how I can organize everything. I can talk about representation theory of this guy. Once I do everything, on top of it, I ask, what about parity? What about time? Are they symmetries? If they are, how do they act? Good? So for now, we just put the study of parity and time on hold. We'll come back to this. We'll just look at the representation theory of this. We'll discover spinners, and then we'll have to come back and see how do parity and time act on spinners. All right. So this piece, SO plus D comma 1 restricted Lorentz group, is connected, but it's not simply connected. A space that's not simply connected means that, like, and I drew an example, right? This space is with one hole, well, actually, let's say 2 holes, right? Is connected because every 2 points we can find a path, but it's not simply connected. Simply connected means that if you have 2 paths between the 2 points, you cannot continuously deform them to each other. Another way of saying that is the fact that you cannot deform this path to this path continuously means that there is a loop that you could not shrink. Good? The failure, the fact that you cannot, if the manifold, if the group is such that you could not shrink these loops, that's a topological obstruction. And that's what I meant by saying that you have a one hole. You have a hole whose boundary is one dimension.
And what is the meaning of those holes?
Homotopy theory. Feel free to read up on it. All right. Now, good. So SO3 is connected, but it's not simply connected. It sits inside SU2 that is connected and simply connected. SU2, these are things you could check for yourself. It's very easy. SU2 is a double cover of SO3. We'll get there. Hopefully, maybe your homework you'll get, right? So I can already give you a hint as what's going on. We're dealing with a space, with a manifold, SO plus D comma 1, that's connected. But the fact that it's not simply connected will give us this spinor representation. We'll see that in a bit, right? And to organize that, we often put this inside this universal cover. The universal cover, by definition, is simply connected. And we do the representation here as simply connected one. The same way that we do the representation of SO3 systematically, you first put inside the SU2 that's simply connected, then you study the representation of the SU2. We'll see that. I think I'm just jumping ahead. All right. I haven't defined a bunch of things for now. So let's talk about the Poincaré algebra. Any questions actually before? I don't expect you to understand every aspect of simple connected and connected. Well, connected, I expect you to understand what I was talking about. But simple connected, not yet. We'll talk a lot about this. This whole chapter is about that. All right. So, yeah. We'll discuss that. But I just want to say this one basic, it's a philosophy. I'm just trying to tell you before you see it. If you want to study the representation theory, or even better, projective representations, representation and projective representation of a group that is not simple connected, like the Lorentz group, the method to do it is first to put this, embed this inside this universal cover. Universal cover is a manifold that looks like this, but it covers it a couple of times and simple connected. You use the representation theory of the bigger one because they share the same Lie algebra. The representation theory of the universal cover will give you the projective representations of the actual group. So to study projective representations of this, put this inside this universal cover. Does anyone know what it is? I'll say it in a second. What's it called? Spin 3, 1. And then we do the representation theory. Good. Any other questions? So let's go over the Lie algebra. This is a Lie group, right? So an infinitesimal Lorentz transformation will look like delta epsilon mu nu plus omega mu nu. If I'm talking, yeah, okay, good. And then here are the translations. This omega better be an antisymmetric tensor if it is to generate Lorentz transformation. Is that clear?
Is this delta is like
Uh-huh. It's just the statement that I'm taking an infinitesimal one, so it's infinitesimal near this.
So it just like moves it by omega.
Yeah.
Sorry, one question. The antisymmetry of omega is related to the existence of an inverse Lorentz transformation.
Sorry?
The antisymmetry of omega is related to the antisymmetry of the existence of an inverse.
Does anyone know how to show that the where antisymmetry of it comes from? How do you show that this is an infinitesimal Lorentz transformation? What property should it have? It should satisfy which equation? Yeah. So take this, expand it to second order. That will give you the answer. Good. All right. So the Lorentz group, let's focus on the Lorentz group. What is it generated by? It's generated by 3 rotations, right? And 3 boosts. Is that clear? We often, well, okay, so something to keep in mind. In 3 dimensions, we're in this nice setup. When we talk about rotations, the rotation occurs in 2 directions, right? On a plane. So let's say rotation, I can talk about rotation in XY plane, right? Now, in 3-dimensional space, I'm in this nice position where I can think about the same thing as what axis does the rotation keep fixed, right? And that's just some charge QZ that I construct. It's a Z-axis that gets fixed. And the way I construct this is by contracting it by epsilon tensor. So I define, right? This is a 3-dimensional phenomenon. Right? We'll be doing this a lot. But when I say 3 rotations, you could think of them as GXY, GXZ, GYZ, or I can think of them as QZ, QY, QX. And then 3 boosts are KX, KY, KZ, right? So the Lorentz generators, how many of them are there? From the antisymmetry of this matrix, you know that this tensor, you know that it's D times D plus 1 over 2, right? And then the translation generator, the D plus 1. So you have a total of half times d plus 1 times d plus 2 degrees of freedom that describe this Poincare group. And 3 plus 1 dimensions, this is 10. 3 rotations, 3 boosts, 4 translations, 10. Good. Take an infinitesimal Poincare transformation. It will look like that's connected to identity SO, the restricted Lorentz group. Right, the Poincare group. And expand the near identity is identity plus half I delta mu nu, omega mu nu, j mu nu. These are the generators similar to jxy, right? Minus I epsilon p mu. P mu's are translation in space time. These are the charges. I can tell you in advance, you know that, right? These are the charges corresponding to these symmetries. And these are also the charges. If you're talking about a unitary representation, you're talking about the Hilbert spaces, these guys better be Hermitian. All right, so what's the Lie algebra? You will derive this Lie algebra as a homework problem, but basically the idea is this. The translations commute. You can convince yourself of that. Translate. So what is J mu nu? J mu nu, what is, okay, let's see if you guys can follow this. So J0I, what is J0I? Boost in I direction. What is JIJ? Rotation in the IJ plane, right? So boost and rotations do not commute with translations. This is the commutator. You could write it elegantly in covariant notation. You could write down elegantly the notation, the commutators of the generators of Lorentz group this way. This is a very, very important relation. These relations hold for SOP comma Q. This is the Lie algebra of SOP comma Q. What is SOP comma Q? It's a group that preserves a metric that has P minus ones and Q plus ones. Take that metric, call it eta, put it in there, that's the Lie algebra. Good? All right. Let's focus on the Lorentz group, which is this bit. Oops. What is the fundamental representation of the Lorentz group? What does it mean? Can you explain what it means? How did we define the Lorentz group? As its action on, so say 2 plus 1 dimensional Lorentz group, as its action on the metric, which is a 4x4 matrix. So the fundamental representation of the Lorentz group is is a 4x4 matrix that describes to you how it acts on a 4-dimensional vector. It's a d plus 1 times d plus 1 matrix that describes to you how it acts as a matrix on a d plus 1 matrix. Right? You could check that this is a representation of the Lie algebra. It satisfies these equations. And I'll tell you in a second that you recognize this representation. This is the fundamental representation.
Is this the same as representation?
Fundamental. What are the matrices? 4x4. Adjoint representation, what would the matrices be? Dimensionality. How many? Yeah, okay. Hold on. This is just fundamental representation. Yeah. Does anyone recognize this already? You know this. This is like very intuitive expression. I'm gonna say that in the next slide. But hopefully this is clear, right? This is the Lie algebra. I have satisfied, and I'm claiming that this is the fundamental representation. To do that, let me remind you of this thing that I did quickly in the past. The vector representation or the fundamental representation of SO3, right? So what are the generators? Rotation in the XY plane. These are Lie algebra generators. 1 minus 1, minus 1, 1. This is JYZ, JZX. 1 minus 1. There's a 0 in the middle. Hopefully that's clear. You could define these QIs that I just defined. These are the charges that it's the same charge but labeled by which axis does it keep fixed. It satisfies this Lie algebra. You could just check explicitly. They satisfy this Lie algebra. This is the Lie algebra of SU2. So SO3 and the SU2 share their Lie algebra. They're locally similar, the same. So if you exponentiate these guys, you get the standard rotation matrices, right? Cosine, cosine, sine theta minus sine theta, xp of phi. This is this matrix, this is this matrix. So this is SO3. I'm not making things up. Okay? Very good. What does this look like? This is 2 Kronecker deltas subtracted. What does this look like? 2 Kronecker deltas subtracted. And this A the mu nu's are because you're in SO3 comma 1, not SO4. If you put deltas here, you would be constructing the representation theory of SOD. It's the same thing. It's really the same thing. These are the same generators and same story. The thing to have in mind are these 1 minus 1 diagonal things that they exponentiate to cosine theta, sine theta minus sine theta. Now, when one of the legs is like this, is time-like, when you exponentiate, you end up with cosh sinh, as you would in the case of boost. You also recognize that sometimes when you're dealing with SU2, you construct the way you construct a representation theory is that you take SZ and from XY and XX, SX, you construct SX plus minus ISY. Those are the raising and lowering operators, right? And you satisfy this Lie algebra. You could do that exactly for the SO3 as well. These are all the representation theory tricks. We did that before. I think I very briefly commented on the representation theory of SO3. All right. So now this should not look as magical. The vector representation for this. If you exponentiate this, you get the Wikipedia article on the action of the Lorentz group. Yeah, on the dimensional vectors.
But how can you get that fundamental representation without any other knowledge? Like you have.
No, I gave it. I mean, how do you get the? You're asking how did that come up with this?
Yes.
We're going to derive that by the end of the lecture, hopefully. But I just gave it to you. And now we can check. You could check it's a representation, you could check it's a fundamental representation. And hopefully I motivated as well. This is not like this was the motivation for it, right? All right. So this is precisely where we're going. The name of this lecture and the next lecture is how do we construct representations of the Lorentz group? Well, by that, and what we're going to try to do this systematically. So let's look at the conserved charges. This is for you to do as a homework problem, but the conserved charges are P0 is Hamiltonian, Pi is momentum, J0I is the boost, Ki, and Jij, you could write it this way. These are the angular momentum. By the way, these are called angular momentum. In case it doesn't, usually people write them as L's. Lx, Ly, Lz. All right. So what is the Lorentz algebra? I told you this before. I promise. What I said earlier today was that the generators of the the conserved charges. Every time you have conserved. Every time you have Lie algebras and symmetries, your conserved charges that come out of another first theorem will furnish a representation of the Lie algebra. Voila. This is it. These are the conserved charges that you find by doing another theorem, and you can see that they satisfy a representation of the Lie algebra. It's precisely that statement. So what is the representation? Ji and Jj and Ki and okay, sorry. So here are rotations or angular momentum and boost and boost, blah, blah, blah. I'm not going to summarize it, right? It looks like a mess a little bit. The first line is the Lorentz algebra. the Lorentz algebra has this nice structure that's all epsilons. So epsilons hopefully remind you of SU2. There were the structure constants, right, of SU2. So it's tempting to play the following trick. Define Ni plus minus, which is half Ji is angular momentum plus minus IKI. I'm complexifying my Lie algebra. I'm just adding complex boost to rotations. And then I define this Lie algebra generator to satisfy this. This is a repackaging of the first line here. You could check that. This is equivalent to the Lorentz algebra. What did I accomplish? I wrote it as 2 copies of SU2. Right? 2 copies of SU2 because the generator is Nij and Ni plus and Ni minus commute. What did we find? We found that the Lie algebra of SO3, 1 is the same as the Lie algebra of SU2 times SU2. That's why I've been talking so much about the analogy between SO3 and SU2. They have the same Lie algebra. One of them is a universal cover, a double cover, but the other one. Here, what we find is SU2 times SU2 has the same Lie algebra as the Lorentz algebra. Let's wait for this to sink. Let's just pause and see it. This is the origin of spinners, by the way. This is precisely where spinners come from. We found the SU2s, and that smells like left-handed and right-handed spinners. But it's very crucial that this sinks in. It looks like SU2 times SU2 is a cover of SO3, 1. It's not quite true. We'll see that in a second, but almost. I haven't defined cover for you, right? I've just said the words. We'll define. All right, any questions about this? How am I doing on time? Well, with this, it goes better. All right. This is your first indication that Lorentz group has anything to do with 2 spinners, left-handed and right-handed spinners. All right. So a little bit of group theory. We're going to be talking about projective representation of the Lorentz group. Remember that a representation is also a projective representation, where the phases are 0. So what we're going to go for is characterizing all projective representations. That will include regular representations as well. As I said before, the idea is that the projective representation of a group, a set of words. If the group is simply connected, it does not admit projective representation and doesn't have identity. Established identity is not in our group, right? So it cannot be centrally centered. If the identity is not in group, if it's simply connected, it cannot admit projective representation. Good. So the idea would be to put Lorentz group inside a larger group that shares the same Lie algebra but is simply connected. Now that larger group will have representations that you use. It won't have any projective representation. It will have only representation. You use those representations to construct projective representation. You put SO3. SO3 is not simply connected. You put it inside this double cover SU2. SU2 is simply connected. It only has representations, no projective representations. Representations of SU2 give you projective representations of SO3. Good? This is the logic. All right. So we're going to be working with the restricted Lorentz group, right? It has no projective, a Lie group has no projective, I said these words. SOD, 1, Lorentz group does not admit central extension, identity is not in it, so But because it's not simply connected, it will have projective representations. They're called projective representation of the Lorentz group are called spinors. Spinors. Good. All right. So what the hell is a covering space? Let me motivate it by a simple example. A line R is a covering space of R S1. At every point, locally, S1 and R look the same, right? But R is like you go around S once, you don't come back where you start. You don't identify. You go further up. It's like a spring, right? You go further up. You go it's like an infinite spring. You just go like that. So we say R is the cover of S1 because they look locally the same. They're both Lie groups. They have the same Lie algebra because the Lie algebra is just tangent at each point. However, one of them is globally different. S1 is different that as you go 2 pi, you have to identify those 2 points. But R, you just simply don't identify. You keep going. You keep going. You keep going. So that's what a cover is. Cover is a manifold is a cover of the other one. If they locally have the same, if they have the same tangent space. However, the other one is a pancake stack on top of this. It's a pancake stack, right? Because the neighborhood of each, say R, right? When I have this, if I want to project R to S1, I can project it such that the domain that's projected to this guy is just a stack of pancakes. It's a stack of intervals, right? Because the image of this under this is a stack. We say pancakes because usually these are open sets. That's what the cover is. Let's make sure that's it. Actually, let me give you an example right away. I've walked you through this before. SU2 is this group, alpha, beta, minus beta star, alpha star, with this condition. You can write it in this form, cosine theta over 2, theta over 2. You can check that this is just a reparameterization of this. With what variables? Theta runs from pi to 0, phi from 2 pi to 0, psi from 4 pi to 0. If I just looked at this, if I set this to 2 pi and identify psi equal 2 pi to psi equal 0, I would get SO3. I would get the sphere. SU2 has an identification by 4 pi. You go around by 2 pi, you're not quite back yet. You go to the second pancake. You go around, now you identify. That's what it means to say there's a double cover. Locally, they look the same, right? It's just global difference. And the global difference is somewhat trivial. You go around a couple times, right? It's like have the picture of stack of pancakes in mind. That's literally what it is. All right. So SU2 is a double cover of SO3. SO3 is not simply connected. Its double cover is SU2. It also has a different name because come out of these double covers the idea of a spin. It's also called spin 3. It's another name for the same group. They're isomorphic. Now, okay, now I don't have it on my slide, but let me just say it. So, oh, sorry. What is a universal cover? A universal cover is a cover that is simple.
By definition.
If a cover is simple connected, we call it universal. So a manifold that is simple connected is equal to its own universal cover. Good? Everybody's with me?
So R3 is its own universal cover.
Question?
It's just like why, like what makes these two groups so like intimately related in that like if you just like dreamt up a random like not simply connected group, is it always going to have some simple cover like
Universal cover.
cover?
You're asking, is there a universal cover to every non-simply connected
Yeah.
Lie group? Yes. Yes. But instead of, I asked it because the world of Lie groups is kind of wild. Let's just stick to the ones that we care about, right? SON as universal cover is called spin N, right? SO D comma 1 as universal cover is called spin D comma 1. And these are what we're going to discuss in this course. Right? Just one thing. So you already saw that spin 3 is SU2. Does anyone know what spin 4 is? This is isomorphic.
SU3.
The numbers should add up. What is this? SU2 times SU2. This is actually the origin of the representation through the Lorentz group. This is an identity. So, but we're not after spin 4. We're after what? Spin 3 comma 1, right? These two groups are kind of related. And for now, we'll see. For now, we start with we pretend there's no difference between them. We start doing representation through this guy. I'll come back and tell you what the difference is. You'll be okay if you just confuse the two for a while. Yeah.
If I give you a group,
yeah,
a random group,
yeah,
how do you know if it is simply connected one? And second, what is it is a universal cover?
You're asking me. So you're asking me how do you calculate the fundamental group? How do you know it's simple connected? It's simple connected if and only if its fundamental group is trivial.
And if there's no.
That's the definition of it, right? By the way, what is the fundamental group? The fundamental group is well, the fundamental group. Sorry, what's the fundamental group of SO3? Z2. When you put in that 2 means that it's a double cover. It's universal cover, which is SU2, will have 2 covers. What is the fundamental group of SO2? SO2 is circle. Z, hence the picture I drew. Right? Here, the stack of pancakes is infinite because the group is Z. So it's an infinite cover. But here, the group, it's a double cover, Z2. Right? What's the, let me just say this, I get it out of my system. SO3 comma 1. What's its fundamental group? Z2. So spin 3 comma 1 is a double cover of SO3 comma 1. That means that as you go around by 2 pi, you come back to the same point in SO3 comma 1, but not in spin 3 comma 1. You have to continue 2 pi more to come back. So you have an operation which is not identity but scores to identity. What do you call that? Picking a minus sign. What do fermions do as you rotate by 2 pi? They don't come back where you were. They pick up a minus sign. Why? Because as you go by 4 pi, they should pick up a plus sign. They should be identical. We have fermions, which is, there are only 2 options. Bosons after 2 pi, they come back where they are. Fermions, they pick up, sorry. See, bosons and fermions, I'm so sorry. Spin. This is about spin. I haven't told you about the let's go with boson metric. Who cares? I haven't told you this representation. Anyway, so if you go by 4 pi, you have to come backwards. There is no other option, right? There's absolutely no other option. You might have heard of weirder particles in 2 plus 1 dimensions that are neither bosons nor fermions. They are, yeah, anions or
Siemens.
there are all sorts of things. What does that tell you? It tells you something about the fundamental group of SO 2,1. What does it tell you? It's not Z2. As a matter of fact, what is it? Z. SO2,1 is an exceptional case with Z. All the higher dimensional ones is Z2. That's why this weird phenomenon is only 2-dimensional. This non-fermion boson thing is only 2-dimensional. Yeah.
But the double cover then comes from because that thing that you said about pi goes from 2 or pi looks hand wavy. But if you
No, it's literally true.
yeah, but how do we show that it is the
Well, you do your homework. You know how to represent SO3,1. You pick your representation. There's a range of multiple. You will pick a variable that's periodic. You identify by 2 pi. Instead, you identify by 4 pi. You try to prove this is a rewriting of spin 3,1.
so it's not by the group action that you show the
There are all sorts of ways of doing it. You do it the way you want, but there's of course like a lot of years of topology and methods behind this. But I recommend the simplest thing the physicists would do: pick coordinates, write it, and try to change coordinates. That's how physicists do it. Mathematicians don't ever. They just like look at it and say Z. That's how mathematicians calculate this, right? They stare at it long enough and then they say the words. All right. So again, to repeat, oh, we're out of time, and I ran out of time even with this. Wow. All right. So in summary, what are we after? We're after SO plus D comma 1, the restricted group, Lorentz group. What is this universal cover? I just gave you the name as spin plus D comma 1. It's a double cover, right? And I already told you that we're going to be studying the representations of spin plus D comma 1. They give us projective representations of SO plus D comma 1. Good? A little bit of a lie. We actually kind of study spin plus D plus 1, spin 4. And then from that, we build spin. We talked about spin plus D comma 1. Okay? That's actually how mathematicians do it. It's called complexification. It's a trick. It's called complexification. I'm not going to explain the trick, but we're going to just present as if it's obvious. That's just how it is. Right? All right, but I already told you the group we're after is spin 4, which is SU2 cross SU2, and I already hinted at it because we saw that I rewrote the Lie algebra of SO plus 3 comma 1 as Lie algebra of SU2 times SU2. Good. Let me see what other. Okay. Give me 2 more minutes and then I'll stop. Okay. Spin 3 comma 1 has another name. It's SL2C. What was SL2R? Yeah, but which group was it isomorphic to? SL2R is the double cover of SO2 comma 1. Okay, so you see a lot of these are related, right? Spin 4 is SU2 times SU2. All right. I did all of this, but let me just say in words and I'll stop. Now, what are the representations of SU2 times SU2? We know all of them. We know all EREPs of them. You know all EREPs of them. How are the EREPs of SU2 labeled? Spin, it's a half integer, that E-rep representation has dimension 2s plus, or j is a half integer, that the dimensionality of representation 2j plus 1, you know everything about it. So you have one of them here, another one here. So you're gonna label representations of the Lorentz group using two numbers that are half integers. Good? Every time you want to describe to me a field, you have to give me two half integer numbers to tell me how it transforms under the Lorentz group. Now, these are half integers starting from 0. What if this is 0 and this is 0? Trivial representation, trivial representation. What field is that? Scalar. What is half 0? By the way, we write them this way. We write them as 0, 0, scalar. Half 0 is wild fermion. And the one that we'll demystify next time, half is? Anyone else? Any other guesses? Vector representation, fundamental representation. We'll see that. All right, thank you.